I'm just checking to make sure that I am live. There we go. Yeah, I can hear myself, so that's good. Okay, so today we're going to be starting with book 6. You should have. So what are we doing? I always forget to say what I'm doing and who the heck I am. The internet. So I'm Christina. I am a data scientist, and to hold myself. Oh, hold on, let's just do it. Whoops, I'm still viewing myself. Okay. Okay. And this is just me holding myself accountable to show up and live stream for 28 days while I relearn, PyTorch, learn CUDA, and revamp on some concepts I'll be needing for a few projects coming up. So we're on day 4. We started out with some basic introduction to PyTorch, looking at its implementation, going through the beginner notebooks, and now we're kind of beginner notebooks of deep learning for coders, and now we're on 6, and we're going to be going through these notebooks today and just reviewing what's there. You're welcome to join and review with me. And then hopefully we'll get into actually doing some stuff outside of the standard book exercises that we have here, because that's kind of how you learn best. So here, today, we'll be talking about multi-label classification problems that we need to solve. And hopefully today we'll go for the full hour to hour and a half, maybe a little longer, depending on where we stop. But yeah, thanks for joining. If you have questions, leave them in the comment section. And for those new to join, you can find what we're working on the Fast AI course website or in their GitHub. And I will put that in the comment section where you can find the GitHub and for YouTube. And if you're on LinkedIn, let me find it. Okay. So today we're talking about other types of computer vision problems, specifically multi-label classification. So before, we were only classifying into the cat dog problem, which is like the traditional computer vision hello world problem that everyone uses. But now we are looking at a multi-classification. So like when you're doing object detection, car is one thing, blue car is a different thing, right? So it's multi-label. So here, they're going to be walking us through using the Pascal data set, what we mean by multi-label. I don't know why I'm always tired when I get on the stream. It's a long day. Maybe I should do these first thing in the morning when I'm writing my newsletters. And y'all can go through my newsletter research with me. But here, horse and a person. So I guess it's a person riding a horse. Bicycle, car, chair. So they import this, and they're using pandas. And the thing about pandas is, since pandas, we have other libraries like Dask, Polars. I actually pinned a post the other day that was talking about the speed of some of these for computation. And when you're working on large data sets, pandas really just doesn't get the job done anymore. So people have developed faster and faster implementations, but this is going to use pandas since this is just research based. But just know that if you're in an actual job learning context, that there are other packages that will do this if it freezes. And so Here, they're just importing their pictures and looking at the ones that have labels. That is that first label, right? And they are checking and grabbing the file names. And yes, someone probably had to label all those images. I think that's like one of the things we take for granted in data science is we're typically not the person doing the annotation, right? But I know and have seen graduate students like typing in these names of these images on behalf of the research team. So um, thank you to all the people that annotate my data. Now I'm sure there's a lot of companies like outsource it to India, like Amazon when they were doing their cashierless stores. There was really a bunch of people on a computer tagging everything you picked up and put down for the model. Yes, their job is, in my opinion, very hard because you're staring at that screen all day trying not to miss anything. It just has to be so tedious. But AI is not medical. You need the data, and right now, oftentimes, it needs to be labeled to have any value to it. So here, they're going to teach us about constructing our own data block. And so we have a data set, which in PyTorch is a tuple, and a data loader, which iterates through the batch streams of like sets of data that it's loading. So it doesn't load at one time. And um, you have a plural version, which contains a training set and a validation set if it's pulled from the built-in, and same thing with data loader. It's built on top of it. Now, a data block, um, data block, they're going to teach us how to build it. So we create an instance of data block here. And what do? We use and create this data frame, and we set it as a data set, it looks like. I want to confirm that by, um, and then it splits it into train and test. And I'm going to confirm that, like if I do a method on data block in PyTorch. So let's do that. So PyTorch data block. And I want to look at the API documentation. Oh, okay, so maybe it is just a built-in of the API, fast API, yeah, potentially. Yeah, it's just a blueprint to assemble data. So it has blocks, data type, batch, get X, get Y. And you can call the dataset method on it. And that is going to turn it into a data set. So it's just a constructor, right? And so here, it pulls out the first instance from train and sets it up like so. Read a pull. Now let's look and see. So here, get lambda this file name, get y this label. So this is the data block. Get equals lambda our file name, get file labels, data set df, data set stop train 0 is now airplane. Let's just created a shortcut function to get the file name and get the label. So file name, and this is the label as a tuple. So it could be a data set. But it's actually, one of the reasons I know a lot of Python people don't always use lambda is because it's sometimes hard to read what it does. There's like whole books on like Pythonic ways to code that I would highly suggest reading so that you can become a better coder, a better algorithm engineer for Python, like Python tricks and data structures and algorithms in Python. So these two lines are the same as this here, but you understand that it's a function and what it's returning. And so you can just get it, right? So it passes through. So now if I pass through data block dataset this DF, right, it's going to get the X and the Y and save it for us and pull out the next one in line. Or the not the next one in line, but it reran the whole thing. So pulls out a different image. Um, and they just use the split to convert to a path of where it's located, which is fine. All the ways to shorten the lines of code of importing and exporting stuff. So it's really nifty. Okay, so they have different blocks that we can use to construct our data into the right format. And the one to use for multi-label classification problem is their multi-category block, right? So they have an image block because it's an image, and then they have a multi-category block. And so it uses this image package that they say is most common, puts it into RBG mode, gives it a size, and then we have the multi-category tensor that was created. And it basically, I'm assuming this is the category it appears for, or the multi-label category it appears for, but it's not actually pulling out like the label name itself, right? It's giving us a tensor, a vector of options, right? Um, so this represents a spot in the vocabulary of available labels, and right, it's just hot one encoding. You know, I see it saying hot one encoding here, but you know how strange it is that you don't realize what you're looking at when you're looking at it, but you're like, oh yeah, I do that all the time. It's standard practice. What are we talking about? I'm not saying I'm practicing everything, but one of the first things you're taught, right? Funny how that works. And then they use where, and they just get the label right out. So now they've kind of functioned everything up, right? And they're checking to make sure it's all valid. And then they create the block, and then they run it again. And now we get this one, the label has moved. And it's, like you said, loading in a mini batch with tensors. And they're using random resize crop, right? So that everything is of the same size, because matrices, to do all of the operations, you need them to be of the same size. And I think it random resize crops means it also is like choosing parts of the image to focus on at that moment, to learn the different smaller parts of it, right? At this scale percentage. So that's good. So this is the batch of items it's pulling, and it pulled for 3 different columns. This is kind of how we, I guess, turn a custom data set into a data set that we can then run our model on. And so, I don't know, it'd be really cool to pull images from like Instagram and do this multi-label classification on them for marketing use cases. Um, we're going to do binary cross empathy, and that is how we calculate the loss, I think. Um, I feel like my brain dumps information so quickly, or it's used to because it's used to doing a lot of things at one time. That has nothing to do with anything else. Um, so when we have a learner object, the learner contains the model, the data loaders, and the optimizer, resonant 18 layers, right? And the loss function. We already have your data loaders, and we use the built-in resonant model, and we're going to use a stochastic gradient descent optimizer, and that's probably set as defaults if we pull up in here. Yeah, these would be the defaults. So we're changing it to CPU so it can run on a computer like mine. And then training one batch, because remember the data loader makes many batches. And then we're gonna run on this learner that we made, gonna get the model right and get the shape. The batch size was 64, and we're calculating the probability of 20 categories. And because it's a tensor, these should be, I'm guessing, the 20 categories or the flattened categories that we're doing, right? And so we get this activation function, which is the list of probabilities for each category, right? And so we want a lower percentage than some of these are showing, right? But that's really high, and that's really low. It's also why we run sigmoid. Yep. So getting that trace, knowing how to manually get the measure, very helpful. Right. So now we run sigmoid, so we can get those on a scale from 0 to 1 and look at them more objectively, right? And then you can calculate the loss function and add a log to calculate log loss. So binary cross empathy, we're going to get the inputs we just got up here, up yonder, and we're going to do sigmoid on it to put it between 0 and 1, and we're going to get where the targets are 1, the inputs, and then 1 minus the inputs. Run a log on it, right? And mean. And let's go back to chapter 5. Chapter 5 from yesterday, we were talking about the negative log likelihood and the scroll log likelihood. You should have went over this earlier, but I did say we'll come back to it if we need to. So this is what we're doing. We calculate the loss for our chapter. This is what we use. And the reason why we just moved from sigmoid, and this is now a softmax. We need to extend the loss function to work with more than just binary classification. That means we need to classify any number of categories in this case. And there's 37 in this particular notebook. Remember, notebook 5. Our activations after softmax are between 0 and 1, and then sum to 1 for each row in the batch of predictions. Their integers are between 0 and 36 because it starts counting at 0 so to get to 37 points. And then the cross empathy log loss generalizes the binary classification loss and allows for more than one label by example. So it can select between inputs between the actual input and then 1 minus the input. And that's how they're going to treat the binary classification problem. Okay? And so then we get the softmax activations out of it. So that's what we're talking about here. Now, you one-hot encoded all the variables, but we can't directly use the this loss or logsmax, and so you can't actually calculate cross empathy, right? And with softmax, it requires that all predictions sum to 1, because we always talk about 100%, right? So everything has to be this amount of predictive to 1, and it tends to push one activation to be larger than the others due to the use of the exponents, right? However, we may as well have multiple objects that we were confident to appear in the image, so restricting the maximum sum of activation to 1 is not a good idea. By the same reasoning, we may want the sum to be less than 1 if we don't think any of the categories appear in the image. And with this toss, it returns a value of just one activation, a single activation corresponding with the single label for that item. This doesn't make sense where we have multiple labels. Okay, so this doesn't work for multiple labels. So binary cross empathy, which is just the loss with log, provides what you need through element-wise operations. So fancy matrix math. That one day I will sit on LinkedIn and we're going to have a math lesson. Or you'll make fun of me making a lot of math errors while I try to teach a math lesson. Each activation will be compared to the target for each column, so we don't have to do anything to make the function work for multiple columns. So according to, I'm thinking this is one of the authors, broadcasting element-wise operations makes it really easy to work with this because it takes into account the item batches. So if we go back to, I think it's the intro lesson, and just look broadcasting, not this lesson. Not that lesson. Here we go. We want to go up one. So, what is broadcasting again? Automatically expands the tensor with the smaller rank to have the same size as the one larger. So that makes all of the tensors even, which lets us do matrix math, and the element-wise calculation is just that matrix math that we need to do. So because it's built in, it makes it really easy to do these changes to get this type of function. And you don't have to write all of that stuff yourself to make it the right size to be able to do it. It just can do it. So it already, so that we also, again, don't have to make our own binary log cross empathy function, is built in for us in this package. Now, I will say that having these built-in functions is great, but sometimes if you're running something that is just math in one way, like you can put, depending on what you're working on, I'm not saying in deep learning problems, but I've been in machine learning problems where I just needed a regression, but I needed that regression to run faster, and I just rewrote that code in SQL, right? So knowing how to go between languages, depending on what your problem is and what your computational costs and like the whole service you're working in, knowing how to go into the built-in, how it works, and pulling it out can save a lot of computation time. In this case, I don't see running this regular Python saving a lot of time. It could, but I doubt it. PyTorch is already slow for production, so you'd end up rewriting this in something like TensorFlow or C++ or a different language for production. So actually, it proves my point. And it requires that you use one-hot encoding to make it happen, but it doesn't include sigmoid. And that's, you use the one with logics attached to it, or log loss. Okay? Cool. And this is it in action. And it does all of that thinking for us. And I know you guys, the one thing you don't also want to fall into is using everything built in and not thinking about what it does or why, because oftentimes in production it just doesn't work that way. So it's good to really know what and why and how these things work so that you can make your adaptations. Okay, so now accuracy is comparing our outputs to our targets, and it's just making a function for us to do that. And they do the accuracy for the multiples classification, right? It takes in a threshold of 0.5. Sigmoid is true because that's what comes out of. And if sigmoid, it will do IMP sigmoid. I'm not sure what IMP is. Look, I'm missing something. Oh, it's just a variable here. And then check if it's more than that, and it will tell you if it's true, and you take the float domain of it. So what does that look like? Parse allows us to bind a function with some arguments or keyword arguments. So here they set the actual threshold of 0.2, and it takes a partial. It pulls it out, takes 5-6 minutes. Yeah. Issues with checking, having a threshold that's too high or too low. So everything passes versus actually having the right balance. Like tuning your parameters matter. Well, not parameters, it's not parameter for your model. Understanding how to choose the right validation information matrix is important. Okay, so regressions. I like regressions. I've been reading more on regressions for econometrics lately. Fascinating field. Kind of wish that was my degree, but alas, it is not. So it would have been fun studying. So here we're going to be pulling out regression. We're going to be running a regression model. And it has dictionaries, and it has sorting them and getting the paths, and it's going to get the file paths, and it's going to image to pose function, return the path, pose text. So it's going to basically pull out all of the images from this file location, and this is the pixels, and this is the thumbnail size. And guess it's generating from the text and getting the tensor, right? So that's what it does once it gets it. And then you're going to construct the data block with these images using this function here. Well, actually, it's not a coordinates. So they have two different types of blocks, coordinate blocks and data blocks. And so it loads all the data, and now we have this batch of items. Now it creates a learner, and it is giving it a range to work in. And it forces it to work in that range on the y, -1 to 1. And that's our sigmoid function. Yikes. And that is the learning rate and the loss. Took a little longer to run it all. And it looks at the results here. So it did good. And the last one we used, it mean squared error loss for regression models. That's the one that we looked at. And that's what we're looking at here. Yeah. Cool, cool, cool. All right, so next up, training a state-of-the-art model. And they're going to bring us to, instead of using stuff from scratch, no, we are going to train from scratch. ImageNet, called ImageNet Neta. ImageNet, I don't know, it was like little image net. Okay, so ImageNet is 1.3 million images, missed 5,000, CFAR 60. They created 10 classes from a subset of ImageNet, and they did what they always did. They created their custom data block. They told it how to get files. They said there's image blocks, category blocks, which is a single classification. And then they have the transformations they're augmenting to look at the different scales of the images, how they're resizing it to make sure they can do that math. And then they're going to load it into the path, right? And so now they're using ResNet 50, and that's the model, and they're going to create a learner, right? So we have the model. We're going to import our data loader. We have a cross infinitely loss flat that is going to be our loss function, and we're going to look at the metrics, which is accuracy, which built in, right? And fit one cycle, so it's only going to make one cycle. And that took about an hour, I'm guessing. It is considered a baseline. So now they're going to look at normalization. Yeah. When and how to normalize data. So since images, again, 0 to 255, so because it represents the pixels, like the RGB of it all, is typically what they use. So they have one batch, and they take the mean of that batch and the dimensions here and the standard deviation of this, and they run it on a CUDA device, not a CPU, and get this, right? So this data isn't normalized. Okay, sorry, I'm thinking. Um, So now they're going to add normalize to the batch transformations that we do. So they do that here, right? And once they normalize it and they put the data loader in, they run the same mean and everything, these values scale. So now this is between below 0, this is above 1. And to check if changing these values mattered, I don't know, I think I'm missing something. Okay. A mean of 0 standard deviation of 1, okay. Normalized. And they do their loss function, their accuracy again, they run one cycle. There's not much change. Yeah, there's not much change. Yeah, I was wondering that. This doesn't make any sense. But I guess their point is if you use a pre-trained model, you might need to normalize your data to make sure the data you're inputting can match the data that's already in the model, and they can kind of have, again, a normalization and looking the same. Is kind of important. So do that. And that way it'll work out better. But yeah, this one, I was like, this, it wasn't adding up, but I guess they explained. They explained. Okay. So if you use Vision Learner, it's already normalized. If you use their stuff, it already takes that into account. Now, progressive resizing. And it's been used, fast AI is used a lot in Kaggle competitions, so you can take that tidbit and go try to win something because it's fast and it's efficient. But what you can do, excuse me, I always get tired when I sit up to do this. It's like plotting against me. Okay. So the features learned by the neural network is not in any way specific to the size of the image. Okay. Early layers find things like edges and gradients, and later layers might find noses in some sense. Change the size in the middle of training doesn't mean that we can find it. Yeah. But clearly there's some difference between image sizes big and small. And so we shouldn't expect our model to continue to work. Exactly. Yeah, it's transfer learning. To get the model to learn to do something a little bit at a time, we are able to tune the model. This is an additional benefit to progressive resizing. It is another form of data augmentation. Okay, therefore you can generalize better if your models are trained with progressive resizing. So it helps with fine tuning to progressively resize. And so they're going to create a small data loader to use one cycle to fit it. So they're going to do resonant 50 again. They're going to take loss, instantly flat loss, regular accuracy, do one cycle. And this is what we get. But then they're going to fine tune. And what they're going to fine tune is this was the size initially. They resized it. They're going to fine tune that same model. Okay. took longer, and it did start with a higher accuracy in the first epoch, and the loss went down, which means there's much better performance. All right. So basically, by progressively increasing the size, the effect is, which is effectively data augmentation and fine tuning, the model gets progressively better. Good. They're also going to data augment the validation set, not just the training set. So test time augmentation. Let's look at that, which makes sense. Like what you do to the input, you do to the output. I mean, what you do to the first input, you do to the second input. Um, or is it a comparable experiment if you don't? Yeah, so that makes sense. It is a science. You have to keep a base. Okay. Random cropping can also be used for data annotation. No, we have been using that. I'm going to say, didn't we just do that? Okay. Um, this is problematic, however. So if you're using multi-label data sets for multi-label classification, if there are smaller objects toward the edge of the images, that could entirely crop out. Okay. So if you're cropping it and there's smaller images and you're doing multi-label, it'll just crop out those images. Even for problems such as the dog breed, there could be things like the nose that could get cropped out of certain pictures. Okay, so to avoid that, um, you could squish or stretch triangular images to fit the square space, but then you'd miss out on a lot by doing that. It kind of transforms it in the wrong way. Uh, so instead, you select a number of areas to crop from the original image and pass each of them into the model and take the maximum average of the positions for all of the areas that you cropped. So it basically goes, look at this, look at this, look at that, look at that, look at that, average together, and then we'll use that. But it also works for time. And that could dramatically improve the accuracy by making those changes bit by bit. Okay, so this is just their time tested um, um, augmentation, and they get the accuracy for a specific item. There we go. So it gives a good boost of performance with not having to train anything, but will be slow. So 5 times slow isn't always great for production. But again, if you got to rewrite it anyway. So then they had the idea of a mix-up, which people came up with in 2007. Things are so new. Hasn't even been 10 years old, and I'm betting this is now outdated or might not be standard anymore because that happens all the time. I would love to read this paper too. I should just make bookmarks of papers for me to read and summarize. Um, so this is how a mix-up works. Select another image from your data set at random. Pick a weight at random. Take the weighted average using the weight of the selected image with your image. This will be your independent visual, and take a weighted average of the image's label with your image label, and that'll be the dependent. So image 2 target and a label and image. All right, and you select a data set. You get a random is the weight. T is the weight. So T times image, 1 minus image. If they're one hot encoded, right? Sidebar, papers and math. That's just telling us paper. Okay. So we get the image, right? Image, resize, get the tensor float, get that as a float, subplot and plot. Okay, great. Okay, so this one here, they added 0.3 to it. Okay, and 0.3 to this one. So it took these 3% of this one. So it took most of the gas and some of the church and put trees there and trees there. And so that's the mix up. So it should predict 30% church and 70% gas. If you do a linear combination of that hot one encoding, that's what you should get. So the final target should look like this. And you can just do this automatically with their built-in the FastAI API. You can mix up to do that. It's definitely going to be harder to train, so why? So it's basically helping to get a higher accuracy by causing some confusion in the model, because it's harder to do it, so it's going to try to do it most accurately. And since it's 70% gas, it'll probably say gas station. Right? So if you have 80 or more epochs, so it can have enough time to get the better accuracy. They've used it for NLP as well. Fascinating. I guess mixing up sentence structure or phrases and paragraphs. See if it still gets the main idea. Okay, so because this will push it closer to 0 or 1, because of how long it has to train, right? We have to do something called label smoothing. And so they're explaining label smoothing in this section. And actually, I should probably read that out loud. So one issue with mix-up, we no longer have that issue because our labels will only be exactly 1 or 0 if we happen to mix with another image of the same class. The rest of the time, our labels will be a linear combination such as the 0.7 and 0.3 we got in the church and gas station example earlier. One issue with this, however, is mix-up is accidentally making the labels bigger than 0 or smaller than 1. That is to say, we're not explicitly telling our model that we want to change the labels in this way. So if we want to make the labels closer to or further away from 0 and 1, we have to change the amount of mix-up, which also changes the amount of data augmentation, which might not be what we want. There is, however, a way to handle this directly, and that is to use label smoothing. So, label smoothing. So basically, label smoothing is replacing your 1s with a number a bit less than 1 and your 0s with a number a bit more than 0, and then we train it. So we can't train on 0 and 1 as a classification. We just train it on a decimal, right? It makes it less, it encourages the model to be less confident, which makes the training process more robust, and it generalizes the model better. So how label smoothing works in practice. Obviously, fancy paper with the fancy math I'm not about to read right now, um, because I can't do math and code at the same time. Weird, but true at the moment. So practicing your paper reading skills. Nah, I'm good. I can't do it at the same time. It's like a different part of my brain. Like two different languages that mean the same thing and translate, but it's like trying to speak English and Korean at the same time. So like right now, I'm trying to learn Korean, but if I read that math, I feel like my brain is trying to speak English. It's not happening. Okay, so we're gonna practice. And they got their model. They load in their data loader. Data loader's model loss function, which is label smoothing, so that is not 0 or 1. It's like 0.1 or more than 0. So like 0.1 is more than 0. Okay. And they're gonna fit one cycle. And that's what they're gonna do, and that's how we kind of do it. We can run this code ourselves, but again, you have to run it for greater than 80 um, 80 epochs. So that'll take a long time. Questionnaire. So it's slower. Uh, Ooh, so much to remember. Okay, we'll do this for next time. Let's look at collaborative filtering. And this field has changed so much, I'm pretty sure this is fundamental, maybe a bit outdated, because recommendation engines have just come so far. Uh, they've just come so far. Like, I don't know. I've heard so many different people's takes on uh, the recommendation model and how to set it up. And it's an interesting field of science. And I'm going to take a break at 7. I don't think I can sit that long, but we'll still be here for at least 30 minutes longer. Actually, I might as well take a break now since I'm switching notebooks. So I'm going to take a quick break and go off camera. Okay, I'm back. So, collaborative filtering deep dive. And this is recommending similar products, different products, upsell products, everything. And I think the classical data set you typically learn would be the IMDb one and like the Netflix recommendation model. They had that competition way back when. They still have one of the best recommendation engines. I think I haven't read any of their newest papers, but I do know there's a lot of things going on in this space, and it's a really interesting space to work in. So, the foundation of this idea is that of latent factors. In Netflix, we start with the assumption that you like action-packed sci-fi movies, but you never actually told Netflix that you like action-packed sci-fi movies. Really? How would they know if they don't tell them? Well, they never actually needed to add a column to its movies table saying which movies are of these types, and still they typically, have the underlying concepts of sci-fi action movie in an age, right? So they didn't actually do that. So, oops, that hurt. What did they do, right? So if we look at the movie lens data set, I cut myself yesterday and it's healing and I don't have a band-aid. It hurts when I move too much. I forgot about it. Okay, let's not move my hands. So when looking at this data set, they import the movie, the rating, and the timestamp on it, and the user. What we're going to do is this was a cross tabulation of movies and users, right? And so they can select just a few of the most popular movies and the movies users watch the most. And when you want to figure out what movies they might want to enjoy, we need for each user what degree they liked each important category of that movie might fall into, such as the genre, the age, the directors, and all that. So either you like it or you watch the whole thing, or maybe you watch it 2 times. That's all an indication of like, and you can kind of get this array from those actions, right, between 0 and 1. So this has, I believe, a high indicator of like, right? So it's very sci-fi, very action, very old. These are the high indicators that it seems to work with, right? This is this user array. It needs to be high sci-fi, high action, and not very old. And so if you multiply those 2 factors together and add up the results, so dot product forms the basis of matrix multiplication, of course. And you get a 2.14. And you do the same thing with something like Casablanca, very on the opposite end of everything this person wants. And you get a negative 1.6, so you don't recommend it to that user. Okay, so step 1 of this approach is to randomly initialize the parameters, and these parameters will be a set of latent factors for each user and movie, and we'll decide how many to use, discuss what to select, blah, blah, blah. And you can kind of create a, I'm guessing because I just downloaded it and re-uploaded it, doesn't show it, but it's an image of an Excel sheet, right? If you go to their website, you can probably get and run their notebook where they say run it, you'll probably get these images. Actually, I can check to see now if I can get these images to show you. This is collaborative filtering. Yeah. So let's make this bigger. So this is going to be these users and the movie ID and their different ratings. And this is the Skywalker information, and now this is bigger, right? So these are initially random linked, and we can optimize them with gradient descent. So these are the users, movies, random information, random scores, right? Um, since I'll just use their notebook. So definitely can't run this. Let me make this bigger. Yeah. So the second approach is to calculate our predictions. So simply take the dot product of each movie by its users. They're going to multiply this by that. And in an Excel, that's what it would how it works. But you can do that yourself. And when you do that, you get all of these things, numbers here. So if it's a mismatch, it's low, and if it's not, it's high. So this is not a great match, this movie and this user, but like this is a great match, this movie and this user. And that's a really great match. This movie just really get to see this movie. All right. So we can calculate our loss and use the loss function, and mean squared error is pretty much standard to use as a basic starting point. So that's what they did. And so they're going to optimize your parameters using stochastic gradient descent so that they can minimize loss with each step and calculate the match between the movie and the user using the dot product and compare it to the ratings, right? So how do we do that? They're going to load their data. And they're going to merge it with the movie. So this is the user, this is the movie, this is the rating, this is the timestamp, this is the title. And then you're going to get the collaborative data loaders from the data frame. They load that all into the data loaders, and we get all the classes here. You can see the length of the classes, length of the movies. And then you're going to get all of the user factors, which is randomly generated, and all the movie factors, right? And then they want hot and cold these modes. You get the float. And then this one times that hot and cold tensor, you get back this tensor representation. And that is our matrix math. And that is also called an embedding. So embeddings are what runs the world. So embedding, multiplying one hot encoded matrix using a computational shortcut that can be implemented by simply indexing directly. It's a quite fancy word for a very simple concept. The thing that you multiply the one encoded matrix by for the shortcode is the embedding matrix, right? So the model learns the factors, and they create here a random factor of 5. They would compute the gradient loss with respect to the embedding factors and update them with the stochastic gradient descent or any other optimizer that you want to use. And since they don't mean anything, it's random. It doesn't really matter what they are. They just kind of randomly pick preferences for the users in this instance, but there will be factors that go into those recommendations. So collaborative coding from scratch. And they start these classes. Inheritance is the most important part of object-oriented, right? So they created a class and inheritance, right? Okay, so this is the dot product model that it created to do this embedding, like what it's multiplying everything by, and then it forward feeds, right? And yeah, let's say we don't need to You don't often see, well, I'm going to say that. I don't think it's needed in this. It's not needed. Okay. So they write one batch and you get this up. Now, so then they have the model. They can run the dot product of the users in the movies, 50, and they're going to run mean squared error, and we get the cycles is running, and there we go. They want the predictions between 0 and 5, and to change that, you change more the sigma range, right, from the multiple classification chapter, and you can do that. So sigma range right here. So they change the range, and they do the sum, and then they do it again. So the loss is decreasing, which is good. Time is decreasing too, even better. And so what they're saying is we only have weights and we don't have biases. So if you only have a single number for each user that we can add to our scores, and the same for the movie, that will handle this piece of information nicely. So they now add movie bias here. Hold on, I feel like I missed something. Okay, so one bias is that some users are more positive, some are negative in their recommendations than others, and some movies are just plain better or worse than others. For our dot product representation, we do not have any encoding of either of these things. If all you can say about a movie is, for instance, that it's very sci-fi, very action-oriented, very not old, then you really don't have any way to say whether most people will like it. Yeah. So they add in some bias in order to make that adjustment. Following. Okay. We do that, and we actually get the loss further down in the training set and the validation set. Well, yeah, for the validation set, the loss goes back up to all the way here, but not in the training set. So why is that? Why did the validation set's loss go up? Yeah, it started getting worse after 2 epochs. Okay, so it's overfit in this case. And this is weight decay. So many words for every single thing. I swear, it's like a whole new vocabulary. Like weight isn't a weight, or even a weight. It's very yeah. Vocabularies. Oh, why can't we just say L2 regularization, people? Why do I have to learn both? Just call it L2 regularization, but for deep learning. Simplify your terms so I can know. My brain. My brain. Okay. So what is that? It adds the loss function to the sum of all weights squared. Because when we compute the gradients, it will add a contribution to them that will encourage the weights to be as small as possible. So just like L2 representation, small as possible. Help to prevent overfitting. The larger, the sharper dips you have in the loss. The larger you want to narrow parameter, like so. So if it learns on large parameters, all the data will fit the points of the training in the over complex function. Right, very sharp changes, which will eliminate from growing, right? Where are my glasses? I keep forgetting to bring them in after I go out. Sum of squares added to the loss is controlled by weight decay or log L2 regularization. Okay. Now they're creating their own 2 embedding module. And so they're going to teach us how the embedding module works so that we know the magic behind it. So all this does is we create a class T. It takes in the parameter. It takes in a torch module of 1s. Actually, part of me wants to skip this because I don't need to know how it works. Yeah, I'm going to skip it because I don't need to know how it works right now. And I want to make sure I can finish this entire notebook tonight. Because I'm already a bit behind since I didn't do a full day on Wednesday. And I want to do C++ next week, like CUDA programming. Like, why not? I might need to learn PyCUDA instead of the C++ way, but, you know. Children of the Corn. Well, this is not a pleasant movie suggestion. So if you interpret the embeddings and the bias, right? So here we get the movie bias, model movie bias squeeze, indexes, bias sort from 0, and then pulls out the titles. The lowest values in the bias score. Everybody likes Home Alone. Not necessarily 3, though. What it's saying is that for each of these movies, even when a user is very well matched to its latent factors, which, as we will see in a moment, tend to represent things like level action up, they generally don't like it, right? Like I just said that. We like Home Alone, but not necessarily Home Alone 3. I don't like Children of the Corn. This is a bad movie, but I do recommend watching it if you're into watching bad movies. It has the nanny in it, which I think is why I probably ended up watching it years ago. I couldn't even tell you the plot other than she's like goes somewhere and she's a beautician. I don't know. It's a romance. I'm pretty sure. So people tend to not like watching any movies kind of would otherwise enjoy. The highest bias. Titanic. I did not enjoy the Titanic. I think I had to try watching that thing 4 times before I got through the whole thing, but I guess I'm the strange person. Never seen this one, but people like this one. Heard this is great, and this is Star Wars, so of course, so people like these movies, even if it's not in something they typically enjoy. They do have computational linear algebra course, and I think that I might get into later. So this is just plotting. Yeah, it's just plotting. So here we go. Schindler's List, dead man walking. E.T. Still not seen that all the way through. So classic versus pop culture movies, perhaps the critically acclaimed. So I'm guessing this would be pop culture, and these would be critically acclaimed. Yeah. I don't need to guess. Just read the math. Read the math. So, Godfather, classic. Braveheart, classic. Liar, liar, pop culture. Okay, so they obviously have their own built-in collaborative filtering model. I'm not going to say obviously, but that's kind of the whole point of their API on top of PyTorch so that you don't have to do everything. And so you're just going to put all this stuff in, train it, and watch it go down. And actually doing it, this simple stuff doesn't really work for like portfolios anymore. Everyone can do it. So come up with a more interesting thing. They do also find the classics, the ones that everyone likes. And so they're going to talk about embedding differences. So the differences between the two coordinates, something all machine learning is ever doing, or all it is ever doing, is measuring distance from point to point on a graph after converting something non-mathematical into a mathematical data object and calculating the distance. So a 50-dimensional embedding, which we've been doing for all of these, they calculate the difference between them. And so if we're calculating the distance, we can calculate the cosine similarity. And you do that for tons of different model types. And so if there are two movies nearly identical, then their embedding vectors would also have to be nearly identical. Right. Because users would like them would nearly like the exact same movie. There is a more general idea, there's movie similarity, so how similar they are, and that's the distance or the cosine, the distance between this movie and that movie. So bootstrap collaborative filtering model. No users and no history. What do you recommend to your first user? Working on this problem right now myself, so glad they're bringing this up. And yeah, I agree. You just make it up, common sense. Asking questions, yeah, at the beginning of enrolling. Yeah, actually, that would be a good workflow. Now I gotta like message my UI designers. Um, I don't know why I didn't think of that, but I do remember that being on the screens of the first time I logged into like Netflix. Um, yeah, I'm definitely about to message my UI UX team. Um, I know I've done a live stream, but I cannot forget this. Okay. Entrepreneurship, right? All of the craziness. Okay. Thank you. This is why I'm going through this stuff again. You forget fundamental stuff. That should have been a duh. Okay. Right. Feedback loop. Deep learning for collaborative filtering. Now, for deep learning with collaborative filtering, they have get embeds, returns the recommended sizes for embedding matrix of your data based on heuristics. Hold on. I forgot one thing. Okay. So to implement this, you have your embeddings, right? And then you execute your model in sequence. So remember, we did ReLU, goes in between the linear layers. The reason being, since I can't say it off the top of my head, we're going to go look it up because that's the whole point. So I'm going to pull this down and I'm just going to, the whole point is so I can actually remember this stuff and not reference it while I'm building. Not this one. Yeah. So ReLU, rectified union. For every negative number, replace every negative number with a 0. Why can I not remember that? Why can I not remember that? As many times as I've seen this. So you do this, you replace every negative number with a 0, and then you do the activation, right? Okay. I will remember this. Okay, so then you do the collaborative to neural network and it creates the embeddings layer. And you do the forward feed and apply the embeddings cycles. And it still performs, but not, this doesn't necessarily, it's not necessarily improving. Right, it inherits from the tablet module and builds on it. Okay. So I am going to stop here for today. And I would love it if you're watching, if you could DM me and tell me where you are in learning and what you've had problems with as you've studied through this with me, and where you're at. I think that'll be cool and a bit fun. And we'll pick up from 9. I want to get through the NLP stuff more than I want to get into the stable diffusion stuff. So I'm not doing stable diffusion work right now. Yeah, so I'm not getting to Keras and stable diffusion and latent diffusion and attention transformers. So I want to finish out. So this is, the numberings are off. The notebooks are different from the book chapters. So I want to finish off this. And so we'll finish off that hopefully tomorrow and go from there. Please, DM me if you have questions on what you're working on. Feedback. Join the newsletter if you like quirky data science stuff. And I will see you guys tomorrow.